Swayam Prabha. Digital India. Educated India.
We now start our discussion on the next module, module 6, which concerns memory management. Now you see, whenever some processes are running on a computer system, one of the very important resources the processes will require is memory, because unless a program is loaded into memory, the CPU or the processor cannot fetch the instructions and run them. Okay? So, memory is a very important resources which has to be shared by the number of different processes. So, here in these lectures under this module, we shall be starting with our discussion on how this memory can be shared or allocated to the different processes and what are the different other issues that come into the picture. Okay? So, we start with some of the basic concepts of memory management. As I said, the first thing that we need to look at is the basic mechanism by which programs get executed on a processor, on a CPU. So, as you know that there is some kind of a storage hierarchy that exists in a computer system. We have the processor, we have the main memory, we have the secondary memory. Of course, there are other components of memory systems, like there are cache memories sitting between processor and main memory, but the cache memory is normally not visible to the processor, means it is hidden by the hardware. But whenever we think about a program, the program after compilation, when you create the object code, they are typically stored in the secondary memory, let us say on the disk. So, whenever you are wanting to run a program, the program gets fetched from the disk into main memory and only then it can start execution. So, this is the first important thing you need to remember. A program must be brought from disk to main memory before it can start execution. So, main memory is a very important resource that is required for a program to execute. And as I said, processors cannot access the cache memory directly, cannot access the secondary memory directly, only it can access registers and main memory. Registers are inside the processor itself. There are instructions which can directly access and manipulate the registers, and main memory you can access data from the main memory. These are the only storage locations which a processor or the CPU can access. And as I said, the other memory components like cache memory or secondary memory, they are not directly visible to the processor. And you think of a main memory, let us say this is my memory, main memory, let us call it MM, and we have a processor, let us say CPU. So, during execution of a program, most of the time the CPU and the memory, they interact. So, CPU sends something to the memory and memory will respond something in response. Now, the memory unit sees two different kinds of requests coming from the processor. First is a read request. So, how is a read request look like? Some memory address is coming, whatever is the content of that memory address, that will be fetched and it will be returned back to the processor. Now, this read request can be coming during the fetching of an instruction or during the fetching of a data during execution of an instruction. For both these cases, this read request can come. And there can be write request also, which can only come during execution of an instruction. For a write request, you have to send the memory address and also the data that you want to write. So, now the memory unit will see that a memory address is coming and also a data to be written is coming. Of course, you may be knowing that the interface between the CPU and the main memory, there are multiple buses, address bus, data bus, control bus, they take care of all these things. And the other thing is that in all modern day computer systems, there are multiple processes running at a time, which means in memory multiple processes are loaded at the same time. So, there is an important need for memory protection. A process P1 should not be allowed to write into the area of process P2 and of course vice versa. So, some kind of memory protection has to be enforced, and all these things concerns memory management. How memory space is allocated to the different processes, how do we protect access to the memory locations and so on. Okay. So, let us look at a simple memory protection mechanism first. We use two different registers, base register and limit registers. These are two new registers that we include inside the processor. Now, what we are talking about is that each process, if we look at a process as a block, with respect to Unix like process, we said that a process can have multiple regions. Some of the regions we mentioned: text region, data region, heap, stack, right. So, a process will be having some address space. These text, data, heap and stack combined constitutes the address space of a process. A process will be having some size. This is the size of a process, let us say. So, this process, its address space, they have to be mapped into some locations in main memory, because they have to be loaded in main memory before the process can execute. And memory protection means, as I said, a process should be allowed to access memory locations only within its own address space, not outside. In memory, my process is loaded, I should be allowed to access only within that boundary, not outside that. To start with, let us start with by keeping things simple. Let us assume that a process occupies contiguous locations in memory, which means this is my memory location, this is my memory unit. A process is allocated space as a single chunk somewhere in memory, contiguous or continuous consecutive memory locations. Now, we see that there is a simple mechanism. If there is contiguous memory allocation like this, we can provide memory protection by using two special registers, base register and limit register. Let us call it BR and LR. Basically, BR will tell you from where this starts and LR will tell you how long is this. So, when you specify BR and LR, it will define the boundary of your address space, from where it starts and what is the size. Okay. Let us see. Suppose this is a snapshot of a number of processes in memory. Typically in memory, there is a portion which is occupied by the operating system. Some of its essential routines, the interrupt vectors, other things, they are stored there. And the different processes may be allocated different spaces. So, here let us assume there are 3 processes 1, 2 and 3, and there is some space at the end which is not allocated yet, free space. And the addresses of the bytes are shown by the side starting from 0 to something. So, we assume the process 1 starts with address 256000, process 2 starts with address 300040, process 3 with this address and so on. Okay. Let us assume that process 2 is currently running. What the operating system will do before the process 2 starts running, it will load the base register BR with the starting address of that process 2 in memory, which is okay, there will be another 0, which is 300040. This is the starting address of the process in memory, and limit register will contain LR will contain the size of that process. See here, process 3 starts from 420940, process 2 starts from 300040. So, if you subtract, it becomes 009021. This is the size of P2. So, LR will be loaded with the number of bytes in process P2. So, operating system will be loading these registers before it transfers control to process 2 for execution. Now, loading of this LR and BR registers is clearly a privileged instruction, because if it is not a privileged instruction, then a user program can also change LR and BR values and can access anywhere in memory. The idea is that there is a hardware mechanism by which you are not allowed to access any memory location outside the boundary defined by BR and LR. How? Schematically we are showing here. Just look at the diagram below first. CPU, you have the CPU here, you have the memory here. Just think about it, whatever is in between, CPU is not concerned about that. CPU wants to access some data from memory, either it wants to read or it wants to write. So, in either case, it will have to send out the address of a memory location. So, the basic thing CPU sends out is a memory address. Okay. You have the limit register, you have the base register. Now, one thing, whenever a process or the object code is created by a compiler, the process is created, that means the instructions are created assuming that the starting address is 0. From 0 up to some maximum, that is the address space of the process. But in memory, the process can be loaded from anywhere you want, it may not be starting from 0. Let us say it is getting started from memory location 1000, let us say. So, when the CPU generates an address, it is with respect to 0. Limit register contains the size of the process. If the size of the process is k, you load the value k in the limit register. So, what you check first, whether the address the CPU is generating, that is with respect to 0, is less than k or not. Less than k means it is within that limit of that process. That process maximum size is k, maximum 0 up to k minus 1, whether it is within that limit. If it is no, means you are trying to access some location outside. So, you generate an interrupt or an exception. This is done by hardware automatically. There is a comparator circuit which automatically compares the address with the value stored in the limit register. If it is not less than, an exception will be generated, control will be transferred to the operating system will be generating some error message and will stop the process. Okay. Well, now suppose it is yes, it is fine, then base register will contain the starting address. Let us say here it will be storing the value 1000. So, whatever address CPU is generating, 1000 will be added. This is an adder. 1000 will be added to the address and that will give the actual physical memory address. This is how the thing works. So, basically every memory address which is generated by the CPU when normally a user program is running, that means in the user mode, must be checked as this diagram shows against the values stored in base register and limit register. And this checking is not done by software, it is done by hardware. And as I said, if you load arbitrary values in the BR and LR, you can access anywhere in main memory. So, users should not be allowed to do that, right. So, instructions to load these registers are privileged instructions, only the operating system can do. Okay. Fine. Now, some very important concepts come in here. There is a concept of logical address versus physical address. Like as I said just now, when the compiler generates an executable code, the executable code is generated assuming that the starting memory address is 0, but it is not real, right. Actually, it can be from anywhere in memory, but compiler does not know where to load it. So, it generates starting from 0, and this is referred to as the logical address space of a process. This is not the real address space in memory, but logically speaking, starting from 0, this is my address space. Let us from 0 up to 5000, this is my total address space. Okay. So, when the process or the program is loaded into main memory for execution, well, depending on the available memory locations, it can be loaded anywhere in memory. Suppose it is loaded from address X, from address X onwards. This is actually where the process gets loaded in memory. This is called the physical address space. So, you see there is a gap, there is logical address space on one side, there is physical address space on the other side, they are not the same. Logical address space assumes that the addresses start with 0, physical address space addresses starts with some value x. CPU generates an address which is with respect to logical address space, because CPU does not know where the program is loaded, it still assumes it is from 0. So, CPU generates something called a logical address, it has to be translated into a physical address. So, logical address space to physical address space translation is one main responsibility of the memory management unit. Okay. So, to summarize, we have logical addresses, we have physical addresses. Logical addresses are those which are generated by the CPU, and these addresses are typically starting from 0 because it is the logical address space of the process. Because this logical address space has nothing to do with the memory addresses where it is stored, these are sometimes also called virtual addresses. And physical addresses are those which refer to actual main memory locations, addresses of the actual main memory locations. So, as I had said, logical addresses will start from 0 up to some maximum value, but physical address will start from some value, let us say x, up to some maximum value. So, this memory management unit which is sitting in between has to do the translation from logical addresses to physical addresses. This is one main responsibility of the memory management unit. Okay? Fine. Let us look at a simple memory management scheme first. In the next lecture, we shall be looking at a slightly more sophisticated memory management scheme. So, we consider a scheme which is very similar to that contiguous memory location using BR and LR, but here we, instead of base register, let us call it a relocation register, in short RER. See, what is the meaning of relocation? See, some instruction compiler generates an instruction with respect to address 0, but the instruction is loaded in memory starting from address x. So, when these instructions are executed, some value of x has to be added to some load and store instructions to get the correct memory addresses. These are called relocation corrections. So, we shall see how with the schematic diagram how these are done. Basically, the idea is that when the CPU is executing a program, so it is fetching instructions from memory, executing them. Some of the instructions may be writing back the results into memory, but for every instruction the CPU is fetching means let me say in this way, for every memory address the CPU is generating, that memory address may be for a read, may be for a write. Read can also be present for instruction fetch. For all such memory address that is transferred, the contents of the relocation register is added to the logical memory address that is generated by the CPU. So, basically the logical address that is generated by the CPU, you are adding the value of the relocation register and you are getting the physical address PA. This is of course for simple contiguous allocation, assuming that my whole process is in one contiguous place in memory, and this translation, adding the content of relocation register to get the physical address, that is done dynamically during execution. This is also referred to as execution time binding. Binding means you are binding a logical address with a physical address, that is binding. Okay. Schematically it looks like this, exactly what I said. So, in the central part in the green box, this is your memory management unit MMU, and inside MMU among other things you have the relocation register. So, what we are assuming is that let us say we have the logical address space which starts from some address 0, let us say it goes up to 4999, total 5000 bytes. Now, in main memory, let us assume that the place where the process is loaded, this is the address space, the starting address is 12,500, let us say, and the last address will be whatever 12,500 plus 4999, whatever is the value, this will be the last address. Now, what the operating system will do before this program is given control for execution, it will load this RER relocation register with the value 12,500. So, what will happen? All the logical addresses that are generated by the CPU, this will get added with 12,500 and the physical address will be generated. So, for example, if the CPU address that is generating is 432, 432 will get added with 12,500 and the physical address of 12932 will be generated. And this will be done for instruction fetching, also for data read, data write, all memory accesses. Relocation means, see, now the advantage you gain is that your program, which here I have shown to be loaded from 12,500, suppose later on due to some reason you want to shift this program to some other place. Let us say you want to shift the program from address 18,000. So, the only change you will have to do, you will have to replace the content of RER with 18,000. The program remains the same, no change required in the program. This is what is meant by relocation. You can move a program around in memory and logical to physical address translation will be done by someone else. Here it will be done by the memory management unit. Okay? Fine. Now, there is a mechanism called dynamic loading and linking, which are some related concepts. Let us talk about this. First, dynamic loading. Dynamic loading means, loading refers to moving a program from secondary memory to main memory, that is loading. So, what we are saying is that we have your secondary memory here. Inside your secondary memory, somewhere, let us say it is a disk, on the disk your program is stored, and this is your main memory. So, when execution starts, this program has to be loaded from secondary memory into main memory and then executed. Now, dynamic loading means, it says that you need not load the whole program into memory, only load the portions which are necessary, because some portions may not be required at all. There can be some portions which refer to some error routines. Only in case of errors, those functions will be called. So, if there are no errors, they will never be called. So, why load them into memory unnecessarily? So, the idea is that the entire address space of a process need not be loaded into memory. You load a function or a module only when it is called. So, only when you call a function, load the code for that function only during that time. Obviously, this will result in much better memory utilization, also faster, because you will not have to load every time in memory. Loading takes time, right. So, as I had said, this mechanism will be very efficient or very useful when good parts of the code, significant parts of the code are for handling exceptional cases like errors, some other situations, but normal execution will, let us say, will limit to only 30% of the code. So, only those 30% of the code if you load in memory, most of the time that will be sufficient. Now, to implement this dynamic loading, in general you do not need any special support from the operating system. Just by designing a program in a proper way, you can implement it. Only the operating system can provide some libraries through which you can have dynamic loading. Okay. Dynamic loading is a standard feature in almost all systems today. And the other related thing is dynamic linking. Dynamic linking means, suppose there is an instruction call to a function, let us say XYZ. This is a program which is calling a function XYZ, and the function XYZ is somewhere else. This is XYZ. So, if you look into memory, this XYZ will be stored from some memory location. So, in this code, instead of XYZ, that address of that XYZ has to be stored somehow. So, how do you know where is that address? This process is called linking. I want to link a function with the calling program. Call XYZ, the address of XYZ has to be put in place of XYZ, so that call to that address I can directly call by mentioning that address. Now, dynamic linking means that this linking I can also do at runtime. So, there are many ways to do it. One popular way is to use something called stubs. So, basically what we want to do, we want to link some system library. Let us say this XYZ is one of the system library function with my program. This is referred to as dynamic linking if it is done at execution time. Normally, this linking is done by the compiler, and that is called static linking. When the object code is generated, the linking is done and everything together, that is my object code. But if I say that I need dynamic linking, this means this calling to XYZ and getting the address and linking them, that will be done during execution. So, one common way and popular way is to use small code segments called stub. These are small pieces of code in the program. Whenever, see, wherever in your program there is a call to XYZ, you add a stub here. Stub is a special small code which initially contains the name XYZ. Later on, when you are trying to call this function, that stub will identify that you are trying to call. Then it will make a request to the operating system. This XYZ function module will be loaded into memory and the address of the memory will get replaced here. Something like that will happen. Okay, I am not going into detail. So, basically what I am saying is that the stub initially contains the name of the routine to be loaded, but after the routine is loaded into memory during execution, the stub will replace itself with the address of the routine, okay, and execute it. This will be done, right? Okay. Now, so far we talked about contiguous memory location. Let us stick to that at least in this lecture, because this contiguous memory location was popular during the first generations of computer system, first generation of operating systems. It was sometime in the late 60s and the early 70s when the multi-programming kind of operating systems first they emerged. So, this contiguous memory allocation scheme was used. Now, some of the basic ideas in this contiguous memory allocation, let us discuss now. Basically speaking, in the simplest case, the memory space is divided into two segments or two partitions. In one partition, there is some portion of the operating system which is loaded, and the other partition is reserved for the user programs. The operating system, that partition, no user program can be loaded there. Now, in this part, which is sometimes called the resident OS because it is always resident in memory, typically it is stored from low memory addresses, starting from address 0 in memory up to some maximum it is stored. So, the essential operating system functions and the interrupt vectors, whenever some interrupt comes, exception comes, which function to call, which interrupt service routine to call, those service routines are typically stored in this resident OS part. Okay. And user processes which are stored at higher memory addresses up to some maximum. So, there can be one or more user programs loaded in that part. And the point is that whenever you load a process or a program, it must be allocated contiguous memory segment, not that half in one place, half in some other place, not like that, all together in one place. Okay. Now, for contiguous memory allocation, already we discussed memory protection can be done using the same base and limit register scheme. So, the CPU will be, I am repeating once more, CPU will be generating an address which is in fact a logical address, LA logical address. First to check whether LA is less than the limit register value, which is the size of the process. If it is yes, fine, add LA with the content of the base register. Okay. In this case, you can also call it relocation register RER, because they function very similarly, and LA plus RER or BR will generate your physical address. So, in this way you are providing memory protection, because if you are trying to access any memory location outside your limit, an exception will be generated. You are not allowed to access anything outside your region. Okay? Fine. Now, in general you can have multiple partitions. Multiple partition means something like this. Suppose you have a memory map here. So, one part of the memory will be occupied by the resident operating system, the remaining part is available with you. There can be multiple processes, process 1, process 2, process 3, and this may be say empty. This is so called multiple partitions. There are multiple partitions, multiple processes can be loaded. Now, in this example, the example I have shown with 3 processes, let us assume a scenario of where the process 2 has finished execution. So, what will be the scenario now? After process 2 has finished execution, it will look something like this: OS again in one part, P1 here, P3 here, this is available space, this is also available space, right. Now, suppose another new process comes P4, which is smaller in size. So, this scenario can look like this. Again OS in the first part, P1 here, P3 here, this is free space. Now, in the place where P2 was there, P4 is smaller, I said. So, P4 will occupy some part here and the remaining part will be again free space. So, now let us see what is written here. Multiple processes reside in main memory, fine. When a new process arrives, it is allocated memory out of available free space. So, here this space released by P2 was free. So, P4 was allocated there. When a process terminates, like here P2 terminated, it releases the memory that was occupied by it. This results in a number of holes in memory. Holes are nothing but chunks of free spaces. Like in the last case, you see there is a hole here, there is another hole at the end. So, in general, when the processes comes and leaves, there will be multiple small holes scattered all through the memory space. Okay. So, hole is basically a block of available or free memory space. With time, as processes arrive, processes finish, a new process arrive. So, there can be holes of various sizes and they may be scattered all throughout the memory space. So, operating system needs to keep track of 2 things. It will maintain some tables. Like the first thing is with respect to allocated partitions. Like for example, in the starting case, it will maintain information about the partitions, let us say P1, P2 and P3. So, it can store the corresponding values of base register and limit register. So, what is the starting address in memory and what is the size? So, it can maintain this information. Similarly, for the free partitions or holes, it can maintain another table. So, all the holes, starting address, size. So, hole 1, hole 2 and so on, it will maintain information. So, basically operating system has to maintain a number of such tables. In these tables, it will keep track of all these things like what are the processes which are currently in memory, which are the free spaces which are currently there in memory, and I said the free spaces can be scattered through in terms of holes. Okay? Fine. So, let us take an example here diagrammatically, whatever I was trying to draw. So, initially let us say this was the scenario, process 5, process 2, process 8, 3 processes were there, process 8 finished. This is the scenario, this is now a new hole. process 9 comes, it is allocated space from somewhere here. So, process 9's come here. So, the hole becomes smaller. Now, process 10 comes, process 10 is also allocated space here. So, this hole becomes even smaller. So, like this it happens dynamically, the holes and the processes change their states in memory. So, at any given point in time, for example, this is the given point in time, there are 4 processes and 2 holes in memory. Okay? Fine. Now, the question arises, if you just go back to the previous slide, that at any given time there can be multiple holes in the system. Like for example, when this process 9 arrived, there are 2 holes to choose from. There was a hole here, there was a hole here. So, how do you decide where to allocate space for process 9? There can be multiple strategies you can follow. Okay? Let us see. Suppose there is a request for a process, a new process has come and it is requesting for a block of size n, n is the size of the process. And what we are saying is that, let us say at any given time, so I am drawing a picture of memory, let us say at any given time, there may be holes of various sizes. Let us say there are 3 holes here. Let us suppose the size of the first hole, let us say 20 kilobyte, 20k, 20 kilobytes. The size of the second hole is let us say 10 kilobytes, and the size of the third hole, let us say it is 50 kilobytes. Let us consider a scenario like this. The first fit algorithm, these are 3 alternate algorithms we are talking about. First fit, it allocates the first hole that is big enough. Let us say there is a request, suppose n is equal to let us say 5k. So, the first hole of 20k, that will be big enough. So, the process will be allocated space within the first hole. Okay. But suppose n is let us say 25k. So, first hole is not big enough, second hole is not big enough, third hole is big enough. It will be allocated in the third hole, right. So, it will sequentially search through the whole table, the table containing the whole information. It will identify the first hole where space is available, it will allocate there. This method, because it always searches from the beginning, it is of course easy to implement, but it may result in small fragmented hole. Like this 5k, that 20k becomes 15k. Say again there is an 8k request, that 15k becomes 7k. So, small size fragments may result if you use first fit. Okay. Now, next alternative is something called best fit. You are trying to find out the hole where the request for n bytes fits most accurately. That means, here you are trying to find out the smallest hole that is big enough. Earlier you are finding the first hole that is big enough, but now you are finding the smallest hole that is big enough. What does that mean? Let us say you have a request for n equal to 8k. Say among the 3 holes, all 3 holes are big enough, but which is the smallest of them? 10k. it will be allocated to the second hole. So, 10K and 2K will be the additional space that will be wasted. This is what you are doing here. But since you will have to find out the hole that is big enough, so you need to search through the memory allocation table. Of course, unless it is ordered by size, if it is ordered by size, you can use binary search. This method is of course slower than first fit, because you have to search something, make some comparison which is the best match. But the unused fragments that are created here are much smaller in size. For example, in this example 8K, if you allocate to the 10K segments, only 2K unused fragment will be created, right. The last alternative is just the opposite of best fit. You allocate the largest hole every time. Do not try to use the best fit, allocate the largest hole. The motivation is like this: the largest hole may be big enough. If you allocate to the largest hole, still the available space will be big enough. You can use it for some other purpose. But the thing is that you are not utilizing the smaller holes in this method. They will remain like that, and the size of the maximum hole will become smaller, smaller and smaller. Eventually what may happen, a process may come where you will not get enough space to load anywhere in one of the holes, although the total space is available, but in any one hole it is not available. So, in worst fit you allocate the largest hole. Okay. Now, here these holes and other things, you see that some part of the memory is utilized, some part of the memory is not utilized. There is a concept of fragmentation that comes in. See, sometimes what happens, whenever you have a memory allocation, see in the examples I have shown, we have not considered this case. Let us say that multiple partition allocation, there is operating system, resident OS one part, and let us say predefined there are 3 partitions which are defined. This is partition 1, partition 2, partition 3. Let us say initially all the partitions are of size, let us say 50K, 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 50K. The idea is that whenever you are allocating space to a process, it must be allocated within one partition. So, let us say a process P1 comes whose size is 35K. What will happen? Let us say part 1, you allocate it to part 1. So, the process will be occupying 35K, remaining 15K will be unused. This unused space cannot be used by any other process, because it is within that same partition. So, here the idea is that the memory you are allocating may be larger than the requested memory. You are requesting 35K, but according to your policy you are allocating 50K. So, within the allocated space there is some memory part which is not being used. This size difference, this is referred to as internal fragmentation, and this occurs, as this example shows, when memory is allocated in fixed chunks, 50K, 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 something like this. So, internal fragmentation means wasted memory space within an allocated partition, that is internal fragmentation. So, this is one of the problems in memory management, you have to take care of this. And the other problem is something called external fragmentation. Like in the holes you saw that in the total memory space there can be multiple holes. So, I am only showing the holes. Let us say there is one hole here, there is one hole here, there is a one hole here. So, let us say this one hole is of size 10K, this hole is of size 15K, this hole is of size 12K. Now, suppose a process comes, let us say P10, which is requesting a memory space of let us say 18K. So, none of these holes are large enough, right, to load this, but the total size of the holes is 10 plus 15 plus 12, that is big enough, 37K, that was big enough. But because they are scattered, I cannot find a single contiguous space of size 18K. This is referred to as external fragmentation, that the total free memory space may exist, but the free spaces or the holes we call, they are not contiguous. But of course, you can try to address this by periodically compressing all the holes. So, what you do? You can use a process called compaction. So, all the processes you can move to one end of the memory. So, all the free space will come at one end. So, all this 37K, they will all come at one side. This 37K free space will come in one side. Okay. So, like this you can create bigger free space and you can make some process utilize that free space if it is required. Okay. Of course, needless to say, this compaction is a very expensive process. You have to shift so much data and code from one part of the memory to another. And of course, since you are shifting around, dynamic relocation is very important. It must be supported by the system using relocation register or something similar. There must be a support for dynamic relocation here, then only you can do this. So, with this we come to the end of this lecture, where we basically discussed some of the important memory management issues, and in particular we looked at contiguous memory allocation. Contiguous memory allocation, we looked at the security issues, how to provide memory protection. We looked at the problem of fragmentation, internal external fragmentation. So, in the next lecture we shall be discussing an alternate memory management scheme, which is in fact more widely used today. There you will see a process need not be loaded in one place in memory contiguously. It can be loaded in small pieces in different parts of the memory. That makes memory management more efficient, and of course, there will be some additional overheads that will be incurred, some more things you have to do for that, and this we shall be discussing in our next lecture under this module. Thank you.